Alright, we are going to talk about the second fundamental theorem.
You can't wear shorts.
I cannot wear shorts. Thank you for the reminder.
We will all email you tonight telling you can't wear shorts.
The American judicial system, no shorts.
You can't wear capris.
Yeah.
You can't be racist.
Go, Leo.
I don't know.
Yeah, he's not. But yeah, all on audio. Here's Mr. Vitra's case file. All right, the first fundamental theorem. We're gonna start there. We remember that the first fundamental theorem allows us to integrate. We talked about this a long while ago. It's been a hot second, but we use it all the time. The first fundamental theorem says if I integrate something from a starting point to an ending point, most of the time a and b, some function, it's going to be equal to its antiderivative. What's the antiderivative of f prime? F. Bless you. Maybe.
Shut up. Okay, stop talking.
Leo. So aggressive this morning. That was my first fundamental theorem. Let's use our first fundamental theorem to hopefully get to a second fundamental theorem. Now, in your brains, the second fundamental theorem will likely look two ways. It'll likely look extremely easy, and it'll look sort of fundamental. It won't seem like there's a lot behind it, but there will be. There's a lot of derivation and a lot of actual usage of the second fundamental theorem that we don't necessarily get to talk about because we're just going to introduce it. A couple weeks we'll throw it back again and we'll see, okay, this is how I see it going off in different areas, but for now it won't look like it's a lot to write home about.
What's the second way we'll see it?
Really there isn't. So I want to start with this problem. Alright, I want to start with this. I'm not laughing. This symbol, this notation means to do what? Take the derivative. This symbol means to do what? Integrate. Let's do this bit by bit. We have to work from the outs or the inside out. So we're going to integrate first. We'll deal with that part first. So integral of t squared is what?
2t.
So this is the derivative that is supposed to be an x, a very poorly drawn x. ddx of, you just told me that the integral of that is t cubed over 3, evaluated from 1 to x. Alright, well, I started with the first fundamental theorem because I can use it right here. This is going to be the derivative of, I'm going to plug in x as f of b minus f of a, so x cubed over 3 minus 1 cubed over 3. 1 cubed, well that's just 1. So this entire thing at the end is 1/3. I've evaluated the integral. Now let me do my derivative step. Derivative of x cubed is what?
Is that 1/3 on the outside of the parentheses?
Yes. 3x squared over 3. The derivative of this 1/3 is what? 0. It's a constant. So I can clean this up. The 3's and the 3's cancel, and I get
Excuse me. So you just cubed it. So I don't understand why you did that. Wait, what? You go back. I am very confused.
dude. It's not to. Listen to the words I'm saying. Hey, I'm gonna go on a soapbox, and I'm not necessarily angry at Jacob, but this is a soapbox moment. Realize that most of the things you miss in this class is because you're writing, you're not listening. I need you to listen to the words that come out of my mouth. I'm putting numbers and things up here as reference. Most of the information literally comes from my mouth to you. This was me simplifying. 1 cubed is 1 over 3. I'm just writing it out to the side. This is a 1/3 as we're going through there. Cool? Now, if I need to slow down as we're going through there, let me know, and I'll write slow. I'll give you more breaks. But you need to listen.
He's just saying that that's 1/3.
Saying 1 cubed over 3 is 1/3. It's not to the power of 1/3. Then I take the derivative of 1/3. It's 0. So I see some weirdness in here, and I'm hoping that we could find a pathway that ignores all of this and maybe just goes from here to here. It literally just cancels them out. Right? What is the opposite of an integral? The derivative. What's the opposite of derivative? So if I have the derivative and an integral, it's literally just the same thing. They cancel each other out. And I'm going to take whatever was up here and thwomp it down in there. That's the second fundamental theorem. The second fundamental theorem says, bless you. This is going to be version 1. We're going to have several versions of this. And by several, I just mean 2. Yeah, we're going to update it in just a minute. If I have the derivative of an integral, and this is going from some value a to some variable x of some function f of t dt. We don't need to integrate it. We don't need to take the derivative. We just look at this, say, great, take that x, plug it in. This is equal to f of x. That is the second fundamental theorem. Yes, ma'am?
So can we not do it with indefinite intervals?
Oh, you cannot do it with indefinite intervals. True.
Wait, why?
Because there are no bounds, so you would have a boundless integral.
Wait, what's a boundless derivative?
Right. I agree with that sentence. See if you can rephrase it, Leo. Alright. So let's look at some examples of this. I thought he was too. I thought he was coming up to like write and say, oh, here we go. You had the entire class's attention. Everyone's like, oh, what's he going to do? That was interesting. These examples are fairly easy. There are a couple curveballs I can throw at you, but I'm going to show them here now. Integral, well, actually, derivative of the integral from, let's go, pi over 6 to x of cosine t dt. I have a derivative and an integral. Basically, in your brain, what are those things going to do with each other? So, I take the x, I plug it in for t, it's equal to cosine of x. Nope, the pi over 6. Look at our previous problem. The 1, did the 1 ever come into play? Right, because when I plug the 1 in, I get a constant. If I take the derivative of constant, what happens to it? Disappears. The bottom number matters nothing. It could be a million. It could be a 2. It does not affect it. Yeah, if it's infinity, we need to panic. We need to freak out a little bit. Yes, ma'am? Oh, great idea. Let's look at another one.
No, you negative it.
Let's go integral x to 4 of t cubed dt. Now, in the great words of the philosopher Leo, he suggested, and I put this in quotes, we negative that hoe. I would agree with that. I think that's a good statement, Leo. Maybe we can find a different way to say it. This, compared to this, is different because the x is now on the bottom. But we know how to deal with integrals. If I want to get on top, I just throw a negative out in front of it. So this is d dx. I don't even want to know. Negative integral 4 to x t cubed dt. And now that, I could have put this negative all the way up front if I wanted to because it's a constant. So that looks like something I can do. So what am I going to get if I apply second fundamental theorem to this? There you go. Second fundamental theorem, fairly easy, yes?
I don't want to say yes because I feel like.
The only other thing you need to know is if you ran into something like this. Play the game that you used to see in your highlights magazines or whatever they are, where there's the two pictures and there's a ball in one of them, and there's not a ball in the other one. How is this one different than the ones we have looked at? It's a function up top. It's not just a singular variable. I now have a function up top. The process is something you've actually already done. It's just a chain rule. I'm going to take this value. I'm going to still flop it down inside. So this is going to be equal to 1 over 1 plus x squared. But when I had derivatives of functions inside other functions, what did I have to do at the end? Listen. If I took derivatives of functions with inside other functions, chain rule. Mr. Vinstra said, functions inside functions, derivatives, plus c. No. I have to do the chain rule with this. So this is 2x over 1 plus x squared. Cool. So our final version of fundamental theorem will look like this. Our second fundamental theorem our version 2.0 or version 2 is this. And this will apply for all of them that we do from this point on. If I have the derivative of an integral starting at a going to some function, that could be any function I want it to be. Right? This works for x, right? What is the derivative of an x? 1. So all of these up here, they were just multiplied by 1. So that chain rule is always present of f of t dt. Well, I just take that function g of x, I plug it into my function that was down there, and then I multiply it times the derivative, which I hear someone whispering, oh my god, that's chain rule. Yes, there's a huge relationship between these two. This is why this is really important, and past that, some accumulation business, that stuff. Cool?
Very cool.
Alright, I want you to try one on your own. This is the one you will try on your own.
Give us a hard one.
No. Here you go. Derivative of an integral from 2 to sine of x of cube root 1 plus t squared dt. Try that one on your own and see what you can come up with.